Hi everyone. My name is Jinyi, and I'm going to introduce my part of this workshop. So my work is aimed on the same goal as Elena did to help improve the feature extraction like LDA did. And I'm using the same technique like Lena introduced before, using the neural network to extract the bottle features. So you may think it like an LDA or something like that. And let's have a look at the features. Here we have a frame of MDCC features with two delta outer. So when we want to use some context information for this feature, so what we do is like Elena said, we stack the features. Now we got a dim like 429. This is pretty high dimension, so we want to reduce the dimension of the feature and make it more condensed. So we're using the neural network to achieve this goal. So what's the targets for the neural network? When we think about it, like we are using the AUD system, so we discover some acoustic units. So we are thinking use the states of the acoustic units as a target for training the neural network. And here is the framework of the neural network. We use the nonlinear hidden layers for training and learning information, and we're using the linear layer to exact the bottleneck features. So when we're talking about targets, we have different ways to generate the targets. Here we have a thing called hard targets. Like we can see, we only focus on one state for each input. So let's think about the drawback. When we were having the state A with a 0.4 probability and with the state B with 0.6 probability. So at this time, the system were going to tell us, let's choose the state B. But maybe in such a situation, we want to keep more possible choices using as our targets. So that's why we're heading for another way using soft targets. As we can see, for the same input, we got more possible choices for the targets. So I think it's more smooth way. That's why we call it soft targets. And here is the actual neural network we are using for the experiments. We increase the depth of the neural network and using more units for each layer. So the bottleneck feature dim we are using here is 40, and the total number of targets we're using is 300. And let's see how the system works. First of all, we have the MSS features, and we train the AUD system with this feature. And this is a baseline performance. We are using the normalized mutual information. And after this training, we got the posterior as our targets, and we use the MSS features as the inputment. So we train the neural network. And since we got the neural network, then we can exact the bottleneck features using this network. And then we got the bottleneck features, then we train the AUD system again. So when we want to have a look at how the bottleneck features look like, here we go. And we're using two different kind of targets. As we can see, if we want to see vertically, the feature becoming more easier to distinguish per frame. So that's what we want. And compared to the baseline system, we can see both the soft targets and hard targets gain some improvements against the raw MSS features. So the winner is soft targets. And we may want to wonder what's the top line for the system. And so that's why we train the bottleneck features with a true label. When we're saying true label, we mean alignments with the phoneme states. So the NMI 38.7, that's a goal for our future work. And if we try to put some technique like language model constraint like Luca introduced before, we can gain slightly more improvement on both soft targets and MSS features. So here is the conclusion. For using bottleneck features, we did gain some improvements against MSS features. So without language model, we gain a little more increase compared to the background language model. But we did this with bottleneck features. So that's what I work. Thank you, everyone.